Welcome back to the active suspension system. In an earlier video, we modeled the system from physics and built its block diagram. In the next video, we simplified that block diagram and found the transfer functions g1 and g2 by series, junction move, and feedback rules. Today, we will reach the same answer using a completely different method, state space. We will write the state equations, build the A, B, C matrices, then apply the matrix formula G of S equals C transpose times SI minus A inverse times B. Same physical system, same answer, new technique. Step 1. Choose the states. Looking at the block diagram, we have two integrators in series. Each integrator stores one state. We name the integrator outputs from right to left. The output of the rightmost integrator is x, the position. The output of the middle integrator is the derivative of x, the velocity. So we set state 1 equals x and state 2 equals x dot. The input is U, the voltage. The disturbance is W, equal to h, the road bumpiness. The output is y, equal to x, which is state 1. Step 2. Write the state equations. From the block diagram, the first integrator turns x dot into x. So the derivative of state 1 equals state 2. That is the first equation. The second integrator is fed by the total force divided by mass m. The total force entering the integrator is c times the quantity w minus state 1 plus k times a times u. Divide everything by m. So the derivative of state 2 equals c over m times w minus state 1 plus ka over m times u. The output equation is simple. Y equals state 1. We have a complete state space model. Step 3. Extract the matrices. Rewrite the two state equations in matrix form. The derivative of x equals a times x plus b times u plus o times w. From state 1 equation, derivative is just state 2, so the first row of a is 0, 1, and the first elements of b and o are 0. From state 2 equation, state 1 appears with coefficient minus c over m. State 2 does not appear, so the second row of a is minus c over m, 0. The coefficient of u is ka over m, so the second element of b is ka over m. The coefficient of w is c over m, so the second element of o is c over m. For the output, y equals state 1, so c transpose is 1, 0, and d is 0. Step 4. Apply the transfer function formula. We use g of s equals c transpose times si minus a inverse times b for the transfer function from u to y. First compute si minus a. The matrix Si is S on the diagonal, 0 elsewhere. Subtract a. The result is S, minus 1 in the first row, C over M, S in the second row. Compute its determinant. S times S minus minus 1 times C over M equals S squared plus C over M. So the inverse is 1 over S squared plus C over M times the matrix S, 1 minus C over M, S. Now multiply. C transpose, then the inverse, then B. The result is Ka over M divided by S squared plus C over M. Multiply numerator and denominator by M to clean up. Ka divided by ms squared plus c. Factor c from the denominator. Ka over c divided by 1 plus s squared m over c. This is g1 times g2. Step 5. Separate g1 and g2 and verify. We need g2 by itself, the transfer function from disturbance w to output y. Apply the same formula but with O instead of B. G2 equals C transpose times Si minus A inverse times O. The O vector is 0, C over M. Multiply. The result is C over M divided by S squared plus C over M. Clean up. C divided by ms squared plus c. Factor c again. 1 divided by 1 plus s squared m over c. So g2 equals 1 over 1 plus s squared m over c. Now g1 comes from dividing g1 g2 by g2. Ka over c divided by 1 equals Ka over c. The result, g1 equals Ka over c, and g2 equals 1 over 1 plus s squared m over c. These match exactly the answers we got in the previous video using block diagram simplification. 2 methods, 1 truth. Let us recap. We took the active suspension system, the same one we modeled in our first worked example, and simplified in our previous worked example. This time we used state space. Step 1. We chose the integrator outputs as states, position, and velocity. Step 2. We wrote the state equations from the block diagram. Step 3. We extracted the A, B, O, C matrices. Step 4. We computed SI minus A inverse, then applied the C transpose SI minus A inverse B formula to get G1, G2. Step 5. We used the O vector to get G2 alone, then divided to get G1. Final answer, G1 equals Ka over C, and G2 equals 1 over 1 plus S squared M over C. Same as before by a different method. 2 paths, same destination.